hardware in the loop validation testing, hill testing. And so I think this is near and dear to everyone's hearts that's done any battery or electronics development. So please welcome Bill.
Thank you and good afternoon. As he said, I am Bill Eccles. I am also not from Archer. I do come from Bloomy Controls, though. I'm not all that jet lagged because I flew on Sunday afternoon so I could visit the Computer History Museum. My dad worked on Whirlwind 1 when he was at MIT back in the early 50s, and I wanted to see what they have and maybe let him describe it to me by FaceTime. Unfortunately, and the next line is not he died, the plane was delayed in Phoenix and we landed late, so I never made it. But that did not stop me from what I usually do when we're landing. I always look out the window, and I'm always fascinated by how quickly the plane comes to a stop. The tires grab onto the pavement, there's a puff of smoke that happens, the spoilers deploy, the engines go into reverse thrust, there's a tremendous roar, we're unceremoniously slammed against the seat in front of us. And I thought to myself, I'm on Whirlwind 1. I'm riding a dinosaur. This is already a museum piece. What you're doing today is developing the next wave of aircraft. It's eVTOL, and it's astounding. It's 100% different from anything we've done so far. Now I have to learn to use this complex piece of technology. Green button. There's the green button, very good. Fast forward from 1952 in Boston to 1992 in Connecticut to the mind of Peter Bloom, who founded Bloomy 31 years ago. In Bloomy's 31 years, we've seen numerous new technologies, from advances in engine and flight controls to innovation in automotive technologies and defense applications. We pride ourselves on being able to keep pace with these advances. And as we find emerging applications, we develop test technologies to help our customers provide their best products to their customers. eVTOL is one area where we're leading the technology with a test system which unifies the aspects of flight control systems and battery systems management. It's called the eVTOL Hardware in the Loop Test System, and I'm going to introduce it to you today by explaining how it's used and why it could be an invaluable part of your development strategy. Now, because I know we come from different backgrounds, let's do a quick review of what I mean by hardware in the loop, and then we'll focus on how we use it for eVTOL. Press hard. We start with the humble closed-loop system. You all have closed-loop systems in your home, in your heating and cooling systems, although based on what I've seen so far in California, I'm not really sure you need them. Your control is the humble thermostat. In a hardware-in-the-loop test system, your thermostat is the hardware. It sends a signal by detecting I'm going to have to explain a thermostat myself real quick. The thermostat detects the current temperature. It compares that to the set point, to the desired control point, and it sends a signal to your HVAC plant, the system, if you will. And then by, again, detecting the temperature, it uses that temperature to complete the loop, all right? In aerospace, the control is the engine control, or the flight control, or the motor control. Now, shown on the left in here, we've got an engine control and a flight control. The control signals from that control provide the aircraft system with the intended motion, the intended temperature, the intended position, whatever it ends up that it's controlling, and the system responds. Sensors then tell the control what resulted. The control system adjusts to bring the plant closer to the desired condition, and the process starts all over again. In this way, the control and the system close a loop. And by looking at the shape, you can tell that is a loop, no doubt about it. And we know that the controller on the left is controlling the system on the right. There's an awful lot of design and test which goes into ensuring that the control loop does what it's supposed to do. But if you're trying to develop the control algorithms, when you turn on the control system for the very first time, you're going to destroy your very expensive aircraft system. Now, if you happen to do that, and you happen not to blow up your whatever it is that you're controlling, please let me know. Well, how do we solve this problem? We solve this problem by replacing the real aircraft system with a model of it. This substitution rids us of the dangers of testing with a real mechanical electrical system, and it instead allows us to test in situations which would be otherwise be impossible, impractical, or outright dangerous to test. And understanding what that model of the system looks like is a little bit easier if we strip it back to the lower level. So let's peer inside each of these components, the control and the test system, and see how they work together. In this view of the hardware in the loop test system, you can see the internals of the control, the hardware, or the H in the HIL, and the internals of the test system, which close the loop. In the control, there are sensor inputs and control laws and driver outputs. The inputs are processed by the control laws, and the control laws drive the outputs. Simple, straightforward. The test system is simply the inverse of that. It reads the outputs of the controls as inputs. It models the effects of those control signals on the system under control and simulates the electrical response of the system as outputs. Now, the control reads these signals and it does it all over again. And it does this as many times per second as is required. And that's the basic composition of a hardware-in-the-loop test system, which tests the real control hardware by simulating the rest of the loop. Now, where things get really tricky is where you're trying to start to integrate systems of systems. How do you integrate a system of multiple test applications together to test all of the systems on an aircraft from tip to tail? Now, in my experience, which I previously worked with Hamilton Sundstrand for 14 years, and prior to that, Pratt & Whitney for a couple of years, and prior to that, the U.S. Air Force for about 6 years, the answer was you ask all of these individual system and component providers to provide their own test systems, and you're going to plop them in your lab, and you're going to somehow integrate all of these systems to work together to emulate your aircraft. And you're going to spend thousands of hours doing it, but that's okay. In the world of $400 million aircraft and defense budgets and so forth, you've got that kind of personnel, you've got that kind of money, you've got the kind of time. On the other hand, eVTOL is moving, and it's moving quickly. You don't have that kind of money. You don't have that kind of time. You're trying to be the first to market. So what do you do instead in order to integrate all of these systems and getting them to talk to each other? And then let's throw another wrinkle into the works. You've got this battery thing, which nobody knows how to deal with on this kind of scale. Now what? Well, I can tell you that you could do the same thing, but you've got to deal with the new technologies, automated flight, battery power, electric motors, regen on descent, and it makes no sense and it makes no sense to spend that kind of money and that kind of time and resources to get one supplier's equipment to talk to another's. Neither you nor your investors want that. So how do we do that? Well, Bloomy has solved that problem, and the solution is available today. This is the Bloomy eVTOL hardware-in-the-loop test system. It combines our decades of experience with battery simulation with our 3 decades of automated scriptable testing, and adds in another decade of hardware-in-the-loop to equal a powerful integrated test platform for every part of eVTOL, from tip to tail, and the batteries in between. Now, because the key to repeatable results is automation, and because scripting is the key to automation, we start with the basics. We start with a test executive, either NI's test stand, or Python, or something else. The choice is yours. This test executive is the same across the entire system. Whether you're testing the battery management system or the flight control computer, it's the same. That's less training for you to do for your new engineers. Mix in the Bloomy Battery Simulator 1200, a cell-level simulator which allows you to stack up to 200 cells to be in series to model a portion of the battery pack or the entire battery pack. And to this, we add simulations of thermocouples and contactors and switching and transistors, and the BS1200 becomes the heart of what's needed to test your battery management system. That's the rack that's shown on the left of our picture here. You can see the BS1200s, those are 12 cells apiece in one rack unit. On the right side, we have what's necessary to complete the picture. To complete the picture, NI and Bloomy partnered together to develop a novel commercial off-the-shelf test platform called SLSC. At first, I doubted that this had been named by the marketing department. It turns out I was wrong. SLSC, the lovely name that it is, stands for Switch, Loads, and Signal Conditioning, and essentially it provides a front end to PXI. PXI cards are small, SLSC cards are large, and they give you the equivalent of what you're probably used to seeing in a VME card in terms of real estate to work with. The SLSC system is also controlled by the same test executive as the battery simulation, and all of these systems communicate using your choice of off-the-shelf technologies, whether it's real-time Ethernet, CAN bus, reflective memory, or something else entirely. And as I said before, the SLSC system provides the signal conditioning for a PXI chassis, which has the usual commodity analog to digital and digital to analog converters. And the PXI chassis is where the model runs under the control of the test executive. Now, because this system is modular, whether it's a system designed for a drone, as this size system may vary, or whether is sized appropriately for a triple channel flight control with a much larger battery pack, or both as would be found in a larger system, the technologies remain the same, and they remain COTS, commercial off the shelf, with a significantly reduced amount of customization required. Now, systems like this were previously unavailable on the commercial market from anybody. The only way to get a common test executive and common hardware platform was to build it yourself, which required an entire test department and infrastructure which, as we all know, is an overhead cost that accountants would rather we not talk about in the first place. Ask anybody in the test equipment department what it feels like to be an overhead cost or a cost burden, and you'll get some idea of what I mean. But now this system is available from Bloomy, where we have focused for 30 years on developing a platform rich in features for mission-critical applications, and where we have the in-house expertise and infrastructure to create and maintain these systems. And if I can toot our own horn for just a little bit, we've gotten pretty darn good at it. So while you've been developing systems which fly, we've been working on making these test systems more accessible, more reliable, and more powerful, so that they can be used to test the most challenging problems you will face as you develop your products. In our 30 years, we have invested heavily in the components required to do this, including the groundbreaking SLSC modules and the groundbreaking BS1200, a 12-cell battery simulator which offers unparalleled performance in a one-rack unit form factor, the SLSC components required for testing military and aerospace controls application, and the through-point panel which simplifies connecting to the control while also providing a breakout box that can't wander off to the lab down the hall. No applause, come on. Everybody knows that breakout boxes grow legs, and then somehow a little post-it note sprouts out that says, in use, don't move. And you may as well not have bought the thing in the first place. And while Bloomy makes the thermocouple, RTD, variable differential transformer, VDTs, rotary, etc., which is an angle or position sensor, and load simulators, there are other companies that make other types of SLSC boards. We have some of our boards in the through-point panel in the BS1200 out front, and Peter, Grant, and I would be very happy to show you more about each one of those. We also make a product called the Hardware and Measurement Abstraction Framework, which disconnects the script from the underlying hardware, reducing the reliance between the two. Now, this seemingly simple concept, which is incredibly difficult to implement, and has taken us around 15 years to pull off in a commercially viable way, future-proofs your test script against hardware upgrades. And it also makes it possible to develop a test script on a desktop system, which will then work seamlessly with a full-size test system like the one in the middle, which may have completely different hardware. We're very proud of this innovation, and we brought it with us today in the form of a mock-up, which you can see outside. The rack stands about this high in the picture, so it's about, I don't know, 2/3 scale or so. And we also have our BS1200 battery simulator and the desktop BMS hardware and the loop test system. Please stop by, and while you're there, let's discuss how Bloomy solutions can reduce your time to flight while increasing your time in flight. My name is Bill Eccles. I work for Bloomy, and we can't wait to hear about your applications.
Thank you. So, Bill, as I was sitting here thinking about this, I've had a chance to work with Hill Systems a couple of times in the past, and one of the things that I found is it's a huge time savings, right? Between trying to put a physical system together and test it, what kind of savings do you see in the development process for a eVTOL application? What do you think?
I don't know that I have a percentage in mind. And in fact, we're dealing in an industry here which is filled with unknowns. In the case of a jet engine, it's going to be very different in its nature from an eVTOL system. But you can imagine that you're going to get a lot more bang for your buck out of a hardware-in-the-loop test system, which, among other things, can run scripted jobs rather at night, provide you the results in the morning, and you can go off and make changes in your control laws and that sort of thing. So you get much more efficient use out of your people, among other things. I mean, that's a huge gain unto itself.
Absolutely, absolutely. All right, any other questions? One way back here. Hold on, I'll get to you.
Good thing he's got long legs.
Do you see any applications of machine learning in these type of systems? Thank you.
That is a very good question, and I'm not necessarily qualified to speak on the area where I think the machine learning is probably going to be best applied, which is in fine-tuning the algorithms in the flight controls. As far as the test system side of things, I do believe that there is machine learning that can be used to help the human along in determining what needs to be tested. It's impossible to test every single corner of the envelope, although we'd love to. But there are going to be optimal points where, based on previous tests, you'll be able to evaluate and say, that if you were doing this as a human, you go, that was a really strange result. Maybe we should test around that area. And if we turn that over to an algorithmic computer, the computer would just go plowing on through all of the points it was supposed to go through and go, hey, these were odd, and maybe that's about as far as it goes. But machine learning could learn from the rule set that this is odd, and we need to investigate a little further and then notice that was still strange, so let's go a little further still. And then maybe that would be used to feed back into the C laws and that sort of thing. Very good question. Thank you.
Awesome. Let's thank Bill.
Great. Thanks.